Hey everyone, and welcome. Today, we're going to dive deep into something that's, well, it's fundamental to how Linux and other Unix-like systems work, the file system. We're about to pull back the curtain and see all the magic that makes it tick. Have you ever really thought about it? How your computer can be reading its own hard drive, a USB stick from your friend's Mac, and a shared folder from a server, all at the same time? How does it handle all those completely different formats and not even break a sweat? So the answer here, it's not just some clever technical hack. It's actually a really beautiful, elegant idea that pretty much changed the game for modern computing. And today, we're going to break down exactly how it works. And it all kicks off with this one, deceptively simple concept. What if we just treated everything like one big tree? You know how on some systems you've got your C drive, your D drive, all that? Well, Unix just throws that whole idea out the window. Instead, everything, and I mean every single hard drive, every partition, every USB sticky plugin, it all gets attached or mounted somewhere onto this one single massive tree. And the very top, the trunk of that tree, is simply called root, and it's represented by just a single /. Okay, so that's the big idea. But how in the world does Linux actually pull it off? How does it get all of these different formats to play nicely together in that one tree? Well, the secret sauce is this really clever layer of software that's basically a universal translator. This is where we meet the VFS, the virtual file system. And that analogy of a universal translator, it's perfect. You can literally think of it as the United Nations for file systems. It lives deep in the kernel, and it creates one standard set of rules. So your apps only have to learn to speak one language, the VFS language. And the VFS itself figures out how to translate that to X4 or NTFS or whatever else it's talking to. And this diagram right here, it shows you exactly what's going on. Down here in user space, that's where your programs live. They make a standard request, and the VFS, which lives up in kernel space, catches it. The VFS then acts like a switchboard operator, directing that call to the right driver for the specific disk format, like ext3 or ext4. The beauty is, your application has no idea what kind of disk it's talking to. It doesn't have to. It just talks to the VFS. Now, for a long time, if you wanted to create a new file system, you had to write some seriously complex code. And you had to write it deep inside the kernel. And trust me, that is a scary place to be messing around. But then, something awesome happened. An evolution that took all that power and brought it out of the shadows and into the hands of regular developers. And that evolution is called Fuse, or File System in User Space. If the VFS is the UN, then Fuse is like getting a massive box of Legos to build your own file systems. It's a framework that lets pretty much any developer build a fully working file system, just as a regular, everyday program. This was a total game changer. It opened up the operating system and let anyone extend its most basic functions. Check out this diagram. It shows the whole switcheroo perfectly. So a request still comes into the VFS in the kernel, just like before. But, and here's the magic, instead of the kernel handling it, the VFS passes it to a Fuse module. That module acts like a secure bridge and sends the request out of the kernel and over to a normal program running in your user space. The whole model gets flipped on its head. Okay, I know this might all sound a bit abstract, but what Fuse allows you to do is just incredible. Let's look at one of its absolute killer apps, SSHFS. So get this. Imagine you could take a folder on some server, maybe halfway across the world, and make it show up on your computer just like a local folder. That's SSHFS. That's exactly what it does. And the best part? No complicated VPNs, no extra server software. All it uses is a standard, secure SSH connection that you probably already use anyway. And I mean, look how simple this is. This one command is all it takes. You're just saying, hey, SSFS, connect to this server as this user, grab that home directory, and just mount it right here on my machine. That's it. It's just wild that it's that easy. But it gets even better, because you can fine-tune this stuff. Let's say you're doing some heavy-duty work, like training an AI model on a huge dataset that's on a remote server. You can add options to make that way, way faster. You can turn on compression to save bandwidth, tell it to cache files locally so you're not constantly re-downloading them, and even tell it to automatically reconnect if the network drops for a second. The point is, you can totally customize this file system on the fly for whatever you're doing. All right, so we've seen how powerful and elegant this whole system is. It's amazing. But what happens when things go wrong? You know, when a disk gets corrupted or something breaks? Well, for that, you need to call the doctor. And that doctor's name is FSCK, the File System Consistency Check. It's the super powerful tool that can scan your file system, find all the broken bits, and try to fix them. It's absolutely essential, but you've got to treat it with respect. This thing is no joke.
And here's rule number 1, the big one. You never run FSK on a live mounted file system. I mean, that's like trying to perform open heart surgery on someone while they're running a marathon. It's just going to lead to absolute chaos. So the safe way, the only way, is to follow these steps. First, figure out which device you need to check. Second, and this is the most important part, you unmount it. Take it completely offline. Then you can run FSK. And when it's all done, you mount it back up.
Now, FSCK gives you a couple of really important options. Think of it as the difference between getting a diagnosis and actually going into surgery. The N flag, that's your dry run. It's like an X-ray. It'll scan everything and tell you exactly what's wrong and what it would do to fix it, but it won't actually change a single thing. On the other hand, the Y flag, that's auto fix mode. That tells FSCK to just go for it and try to fix everything it finds, no questions asked. Super powerful, but you can see why you'd want to do a dry run first, right? And this leaves me to the final, and I mean critical, warning. This is straight from the manuals. Once you've told FSCK to start making changes, you do not interrupt it. Let it finish. Pulling the plug in the middle of a repair is probably the fastest way to turn a small problem into a, well, I guess I'm restoring from backups kind of disaster. So let's just recap. We've seen this beautiful idea of a single file tree and how these amazing layers of abstraction, like VFS and Fuse, give us this incredible, almost magical power. It lets us do crazy things like mount a remote server as if it's right here, and it gives us the tools to fix things when they break. But it all leads to this one final kind of mind-bending question. If you can turn a remote server into a folder, what else could you turn into a file system? People have made Fuse file systems that turn your entire Gmail inbox into a bunch of files and folders, or one that mounts all of Wikipedia. The possibilities are just endless. It really makes you think, doesn't it?